This is going to be a lesson on the transformed trigonometric graphs. Now we already know how to graph the cosine, sine, and tan of theta. But now we want to figure out how we can graph versions of these functions that are a little bit more complicated. So we want to graph all of the functions in one of these four forms. Now let me just quickly go through these four cases. In the first case, we want to know what would happen if we add a constant to the input of sine. In the second case, we want to know what would happen if we double the input to sine. In the third case, we want to know what would happen if we add a constant outside of sine. And in the fourth case, we want to know what would happen if we multiply sine by a constant. Now there's nothing really special about sine. I could have done this for cos, or I could have done it for tan as well. If you're going to want to use trigonometry for anything useful, you're going to want to be familiar with more than just the very basic forms of sine, cosine, and tan. Now, of course, to do this, you're going to want to begin with a unit circle. So let's begin there first. Now in this case, I'm just going to graph the y-coordinate versus angle. So this is going to end up being a graph of the sine of theta. Now the first thing I'm going to do is I'm going to replace the angle theta for another angle, t plus 1 radian. Now for starters, it's going to be useful to have the number 1 marked on our theta axis. Now I want you to know that pi on 4 is just approximately 0.78, so the number 1 shows up roughly here. Now my first instinct when I first saw this was to expect that the whole graph would move to the right like this. But it turns out that's actually not correct at all, so let's just put it back for a moment. Instead, if we're replacing theta for t plus 1, then we could say that theta equals t plus 1. Now it turns out that whenever we replace the input or the output, it actually moves the axis, not the graph. So in this case, the axis is moving to the right by 1. Now if this is counterintuitive to you, let me just go ahead and pick some random point on the graph and just show you that it's true. The first thing I want you to note is that we've moved our axis, so I changed the axis label from theta to t. However, I didn't bother to change the y label because we haven't moved the axis up or down. Now the coordinate of our point is just the distance from here to here on the t-axis. And if I bring back the old axis, we can now see that the coordinate of our point is just this length theta. Now since we just moved this axis to the right by 1, then we can see that the length theta is just the same thing as t plus 1. So we can get rid of these measurements because we don't really need them anymore. Now since we're using the t-axis and not the theta axis anymore, it actually makes sense to replace this theta for a t plus 1. Now there is actually another really good way to visualize this, and to show it to you, I'm going to draw 2 points on the unit circle spaced by 1 radian. So as you can see, these 2 points are separated by exactly 1 radian, and it looks as though this point has a 1 radian head start over the other point. Now the first interesting point is that this point lines up perfectly with the starting y-coordinate of sine t plus 1, and this point lines up with the starting y-coordinate of the original sine wave. So I can get rid of the 1 radian marking, and then I can let both of these points complete a full revolution. I'll go ahead and trace out the path that the green point makes as well. Now as you can see, everything is back where it started, and this new graph we've just drawn on is just y equals sine of t. Now to turn the graph of sine of t into the graph of sine of t plus 1, we just shifted the graph to the left by 1 radian. Now let's keep a record of this on the side and put everything back to the way we began. Now this time we're going to think of the effect of swapping out this theta for 2t instead. Now again, when I was first learning about this, I expected the graph to stretch to double its size. But again, it turns out that it does the exact opposite of what we'd expect. Now just like last time, you'll find that this is not an accident at all. It's because instead, it's the axis that's getting twice as large, not the graph. Now if we shrink the axis back to its original size, we'll notice that the graph compresses rather than stretches. Now after shrinking the axis back to its original size, we're able to fit 2 full cycles on it. Now we can reconstruct these graphs from the unit circle as well, just like we did for translation. To do this, imagine that I had 2 points where one moved twice as fast as the other. Just to be consistent with this graph over here, I'll also switch the colors of the points and graphs. Now suppose we increase the value of t until it hit 1 radian. As you can see, in this time, the first point covered an angle of 1 radian, but the second point covered twice as many radians. Now this makes sense. If we say that the angle covered by the first point is t, then the angle covered by the second point is 2t. Now this means that the graph traced out by the first point is going to be the sine of t, and the graph traced out by the second point is going to be the sine of 2t. Now you can see this. By the time we move t to pi on 2, the y-coordinate for the first point will be 1, and the y-coordinate for the second point will just be 0. Now if this first point completes another quarter revolution, then this point will complete its first lap around the circle. Now it's funny, because on this graph it looks like they're at the same point, but you can clearly see that they're on opposite sides of the unit circle, but both of these points do have a y-coordinate of 0. Now if I just let the first point finish the whole lap, you'll see that the second point will do another full lap in that time. Now again, let's copy this on the right hand side and clear the graph. Now this brings us to our golden rule. Whatever you do to the axis causes the exact opposite to happen to the graph. This important rule is going to help us figure out what happens when we replace this theta for a t multiplied by and added to some number. This first number we call omega, and it measures how quickly the new sine wave rotates. And this second angle is called phi, and it just tells us the angle offset when t equals 0. Now omega does the same thing as this number 2 did over here. It just compresses the graph. And this value phi does the same thing that this 1 did over here. It just moves the graph either left or right. Now suppose you set omega to any number except 1 and phi to any number except 0. In these cases, you're going to both shift and stretch the graph at the same time. Now in this case, you're going to stretch the axis by omega and move it to the right by phi. But we wonder what effect this has on the graph. To explain this, let's just bring out a sketch pad for a moment. Suppose for a moment you are giving somebody a present. Now before giving anybody this present, you're going to have to wrap it. And that involves 2 steps. First you're going to have to put it in a box, and then you're going to have to wrap it. Now once somebody received your present, they're going to have to do the opposite steps in the opposite order. First they're going to have to unwrap the present, and then they're going to have to take the present out to figure out that you've just given them a lollipop. Now just like wrapping a gift is the opposite of unwrapping it, we just said that moving a graph is the exact opposite of moving the axis. Now when we go from sine t to sine omega t, we scale the axis by omega. Then when we go from sine omega t to sine omega t plus phi, we're just moving the whole axis to the right by phi. Now since moving the graph is the opposite of moving the axis, then we must do the opposite steps in the opposite order, just like we did with the present. So I think you can see why this causes a lot of confusion for a lot of people. So let's go ahead and get rid of the paper and just show this. If we start with the graph of sine t again, the first thing we're going to do is move it left, and then we're going to compress it around the origin, so around this point over here. And then we'll go ahead and continue it until we hit the end of our axes. Now if we look at t equals 0, we can see that the y-coordinate of the original is just 0, and the y-coordinate of our new graph is approximately 0.8 for the one I've drawn. So the angle between these two when t equals 0 is just the phase. Now if we let t increase by a little bit, we're going to notice that this point moves a lot slower than this point does. Now since in the picture t is approximately equal to 1, we can see that the angle from here to here must just be omega. So when t equals 0, this angle was 0, and if t increases, we're going to notice that the angle is going to get bigger. Therefore, we can say that the angle between this point and this point is just going to be omega t. Now the sum of both the starting phase and this omega t factor gives you the total angle that we have at any given time. Now we've finished the first part of our discussion about what happens when you replace theta for omega t plus phi, but there is still a little bit more to say. For one, I haven't really shown you how to make these graphs accurately, and secondly, it's not really clear why you would ever do this. These are all things I'll cover in a future lesson, but for now, this completes our discussion on transforming the trigonometric graphs.